And then we are honored to host Dr. Xianyang Zhang in the department, and he earned his PhD from University of Illinois at Irvine Champaign in 2023. Sorry, 2013. He is interested in developing new statistical theories and methodologies for large and high dimensional data with complex structures. His current research focus is deep learning, high dimensional, large scale statistical inference, kernel and distance based methods, and genomics. Please join me in welcoming Dr. Zhang.
Thank you for the introduction, and it's a great pleasure to speak at the STAT Cafe. So today I'm going to talk about e-values and multiple testing. If you have taken my topic course last semester, you already have some idea what I'm going to talk about. So the talk today is based on the joint work with Guanxun Li. He was formerly a PhD student here and then a postdoc, so I guess some of you know him, right? So before we dive into the topic today, I want to give a very brief introduction about my current research interests. So today's topic is mostly related to the first direction that I'm working on. It's about high dimensional and large scale inference. Oh, okay. The first direction is basically about inference where you have a large number of parameters or a large number of units. Typically, this kind of problem can arise for large scale data. And then another direction is about kernel and distance-based method. So I'm particularly interested in understanding and developing methods for these approaches in context of high-dimensional data or non-Euclidean data, say functional data. And I've also been working on genomic applications such as microbiome, more recently single cell. And then I've been also interested in deep learning and trustworthy AI. So last semester, Mr. Anthony gave a talk about watermark in large language model. So that's particularly related to trustworthy AI. And if you want to learn more about my research, you can go to my website. So let's dive into the topic. So first, I will give you a brief introduction about e-values. So in particular, the motivations, the definitions, and some applications. So e-value is a recent notion. It's designed as a replacement of p-values in some statistical inference problem. If you work in causal inference, you probably have heard about e-values, but it's a totally different thing there. So there, basically, e-value is a tool to assess the robustness of one's conclusions to potential unmeasured confounding. But here, the e-value I'm going to talk about is completely different. So originally, e-value was used to tackle the so-called optional continuation problem. The setup is that you have the same scientific problem that was studied, say, by multiple labs. So let's say lab A collected some data about, for example, the effectiveness of a drug. And by analyzing the data, lab A got some promising results, but still inconclusive. And so lab A published the results, lab B saw the results and the data published by lab A, and lab B continues to collect more data, analyze the data, and lab B got some results. Let's say it's still inconclusive, so lab B published the results, and then another lab, lab C saw the results and continues to collect more data. And for when each lab make a decision or come up with a result, the lab also want to use the previous result published by the other labs. So basically, this is a sequential decision-making problem, and there are two questions. First question is when we should stop and claim that there is a finding. So in this case, the drug is effective. And another question is how can a lab combine all the previous results? This is difficult because this is a sequential process, and the results a lab obtained would certainly depend on all the previous results because the lab decides to collect more data when it saws the previous results. So this problem can be difficult if we use the classical, say, statistical evidence summarized by p-values, but it becomes easier if we use p-values. Another problem is the so-called multiple testing problem. We will look into details today. So the setup is that we have several hypotheses, and for each hypothesis, have a p-value, and then you have to make a lot of decisions simultaneously. So in this setup, the goal is to usually control some kind of error measure and then also to maximize the number of discoveries. So first, I will give you the definition of p-values. It's actually very straightforward. So p-value is basically a non-negative random variable will have an expectation less or equal to 1 under the norm. So one question is, how can we construct p-value? Is it possible to construct such a thing? So let's consider a parametric hypothesis testing problem where the data are generated from a parametric family indexed by some parameter theta, and we have the simple versus simple setting. So in this case, it's easy to see that the base factor is an e-value, is non-negative, and you can easily verify that the expectation under the norm is indeed in this case exactly equal to 1. And in the optional continuation problem that I've just mentioned, basically you can think of the e-value at time t as the evidence collected against the non-hypothesis. So usually the larger the more evidence you have against the non-hypothesis. In this case, we have to slightly modify the definition. So here you can think of ft as the evidence or the information we have up to time t. So it contains all the previous results from all the previous labs. Remember, this is a sequential process. And what we require is that the expectation of the e-value obtained at time t, given the prior information up to time t minus 1 is less or equal to 1 under the norm. And then in this case, we can aggregate all the evidence we have up to time t by just taking a product of all the e-values from time 1 to time t. And one can show that this is a non-negative super martingale. And then if we have a data adaptive stopping rule, which is a stopping time, then we can show that the process D stops at tau is still an e-value. So even with a data-driven procedure for stopping, we can still construct a valid e-value. If you use p-value, then it will be more complicated because you have to deal with the sequential dependence. And the question of constructing p-value with a data-dependent stopping rule would be much more complicated. And so with the e-value, how can we construct a test? How can we make a decision? It's actually quite easy. So you just compare your e-value with the threshold. And in this case, if you want to perform the test at level alpha, then the threshold is simply 1 over alpha. So you reject if your e-value is bigger or equal to 1 over alpha. And by simply using the Markov inequality, you can show that the type 1 error is controlled at level alpha. So the nice thing about e-value is that it allows us to perform sequential inference and graduate appraisal of information and evidence. And because by definition, it's about expectation, so it's more robust to data dependence as opposed to p-values, because when we talk about p-values, we usually have to study the tail behavior of the statistic. We have to deal with the distributional behavior of the statistic. But for e-value, you just have to study the expectations. E-value is also a useful tool for combining results. So here, I will talk about 2 scenarios. In the first scenario, we have a data set, and we have multiple methods that could be applied to this data set. Another scenario is that you only have one method, but then you have a tuning parameter in your method. So by using different tuning parameters, you can get different results. So at the end of the day, for the same data set, you can have multiple results. And then the question is, how can we aggregate these results to get a final result? Another scenario is that we have multiple data sets, but then we only have, let's say, one method. And when you apply this method to each of the data set, you can get a set of results. And the question is, how can we combine these results to make a conclusion that is valid for the whole data set when you combine all these small data sets together? So before I talk about some more specific applications, I want to give you a brief introduction about multiple hypothesis testing. So as you can tell from the name, it's about several hypotheses, right? You want to test several hypotheses simultaneously. So let's say you have n hypotheses. You can think of these n hypotheses as the hypothesis for different features, let's say genomic features or maybe different persons. And then for the hypothesis, you can get that as the evidence against the hypothesis. In the multiple testing context, we no longer control the usual type 1 error. We want to control an error measure that concerns all these hypotheses together. So people have considered, say, the family wise error rate, and also the false discovery rate. False discovery rate is a more liberal error measure which can give us more discoveries. And this has been widely adopted in, let's say, genomics. So by definition, it's the expectation of the false discovery proportion. False discovery proportion is simply defined as the ratio between the number of false rejections and the total number of rejections. And this ratio is defined to be 0 if your procedure does not make any rejection. So in the multiple testing context, we want to control the FDR at currently specified level alpha, and then we want to maximize the number of rejections or the number of true rejections. So you probably have heard about some multiple testing procedures. The Benjamini-Hodgberg procedure is widely used. And it turns out that many of the multiple testing procedures can be described in a uniform way. So let's say you want to reject the ice hypothesis if the p-value is less or equal to some threshold t. In the multiple testing context, we want to determine this threshold based on all the other p-values. And the idea here is you want to choose the largest threshold such that the conservative estimate of the FDR is controlled at some level alpha. So here you can see that we have this ratio. So if you reject the hypothesis when its p-value is less or equal to some lowercase t, then the denominator is the total number of rejections. And the numerator here is a conservative estimate for the number of false rejections. So this ratio serves as a conservative estimate for FDR. And here the goal is to find the largest t such that this ratio is controlled at level alpha so that we can make the most number of rejections. And at the end of the day, once you get this capital T, then you reject the ice hypothesis if pi is less or equal to this beta dependent threshold T. So in the literature, there are different ways of estimating the number of false rejections. And here I will talk about the Benjamini-Hodgberg procedure and also the so-called Barber-Candace procedure, which is the idea in their knockoff paper. So in the BH procedure, we are going to estimate the number of false rejections essentially by expectation. So this is the typical histogram you will see if you plot the p-values in a typical, say, genomic application. So you'll see a peak around 0. This is because you have some hypothesis under the alternative, right? So the corresponding p-values would be small. And given the threshold t here, if you make rejections, you are guaranteed to make false rejections because the p-values under the null would be uniformly distributed. So no matter what threshold you use, you're always going to make some false rejections because there are always some non-p values that will be smaller than that threshold. So then the question here is how can we estimate the false rejections? So here for those bars below t, we divide them into two parts. The orange part corresponds to those non-p values, and then the blue part corresponds to those p values under the alternative. So this would be our true rejections, and this would be false rejections. So the question is, how can we estimate this part? In the BH procedure, the idea is that we're going to use expectation. So given the threshold t, if you have n0 non-p values, then the number of p values below t will be equal to n0 times t. So here n0 is the number of non-p values, and we of course don't know that number. So the idea is we are going to replace that by a slightly bigger number, which is the total number of hypotheses. In this case, it's n. So we estimate the number of false rejections by t times n. And in the literature, there is a alternative idea. So the idea is also very simple. It uses the fact that the non-p values are symmetric about 0.5. So usually we assume that the non-p values are uniformly distributed. And in that case, of course, the distribution is symmetric about 0.5. So in order to estimate the orange bars, we can simply use the orange bars that are above the threshold 1 minus t, because the distribution is symmetric about 0.5. So simply we just have to count the number of p values above the threshold 1 minus p in order to estimate the number of false rejections. So with these different estimates of the number of false rejections, then naturally we would have two different FDR controlling procedures, right? And they are both quite commonly used in the literature. Okay, so the next question is, now suppose we don't have p values. Let's say we only have e values. How can we perform multiple testing? And it turns out that it's also quite simple because there is a connection between e value and p value. So if you have a set of e values, you simply define e value to be 1 over the e value, then we can show that the p defined in this way is super uniform in the sense that it satisfies this. So it's a valid p value. So then you can apply those FDR controlling procedure to those PIs. So if you apply the BH procedure to those PIs, then this is the so-called EBH procedure. And people have proved that the procedure will control the FDR. And in this case, the condition we need for proving the FDR control is actually slightly weaker than the condition we require for EI to be an E value. So remember, we require EI to be a valid E value if this expectation is less or equal to 1. But to have FDR control, you only require this summation to be less or equal to n. This is slightly weaker than the condition for being an E value. And another nice thing about this procedure is that it's robust to arbitrary dependence among the E values. So regardless what kind of dependence you have, you can always show that it controls X. So one of our contributions is that we show that many existing FDR controlling procedures, they are indeed equivalent to the EBH procedure applied to a set of E values. And here the trick is that you have to construct those E values in some specific way so that these two procedures can be equivalent. And so in particular, we show that all these procedures, they will be equivalent to EBH procedures applied to some suitably defined E values. So for the BH procedure, remember I mentioned that in that case, MT is defined as n times t, right? And so the cutoff in this case can be defined as this. RT there is just the number of projections you would make if the threshold is little t. And so the E value is now defined in this way. Well, this does not look like the usual E value because we can see that it actually only takes two values. It's either equal to 0 or a non-zero value 1 over t. So basically you can show that if the hypothesis is not rejected by the BH procedure, then the corresponding E value will be equal to 0. And if it's rejected, then because if it's rejected, then pi has to be less or equal to t, right? So in that case, the e value will be equal to 1 over. You can only take two values. And then for the BC procedure, remember, this is the estimate for the number of false rejections. So the threshold will be defined this way, and then we can define the e value in this way. Again, it only takes two values, 0 or some non-zero value. And we show that applying the EVH procedure to these e values will give you the same set of rejections as either the VH procedure or the DC procedure. Indeed, the result for DC procedure has been discovered earlier. And we can further extend this insight by extending the VH and DC procedure. The reason that we want to extend them is because we want to allow a more flexible rejection rule so that we can incorporate some external information. I'll give you some more details later in the last application. So previously I mentioned that usually you would reject the ice hypothesis if it's less or equal to t. But in practice, we want to have some flexibility. So here, the flexibility we can allow is that we can have different thresholds for different hypotheses. Instead of rejecting the ice hypothesis at the level t, here we are going to allow a data, a more flexible threshold. And if it's determined by your data, then it's the data adaptive threshold, which I will give you more details later. So here, fi is some strictly increasing function, but remember, it depends on I. So that means for different hypotheses, we can have different threshold. And then in this case, we can define the cutoff in this way. So here, n times gt, you can think of it as an estimate for the number of false rejections. So if g is an identity function, then you will reduce to the usual BH procedure. And then for this procedure, we have a shortcut implementation just similar to the BH procedure in the sense that it only involves some kind of sorting and then finding some largest k, fulfilling this inequality, and then you just have to find that k in order to get the threshold. And in theory, we can show that this FBH procedure controls the FDR at some level C times alpha. So here, it's not necessarily controlled at level alpha, but it doesn't really matter because you can always choose alpha so that C times alpha is exactly equal to the alpha, to the level you want. And here, the constant C depends on Fi and G, and they are both chosen by the user. So basically, given Fi and G, you can compute your C, and you can derive the level, the actual level, and then you can adjust alpha. And in some special case, say if GT has this form, is the average of those Fi's, and Fi is proportional to a common function H, then C becomes 1, and then the procedure controls the FDR at level alpha. For the BC procedure, we can also generalize it by allowing this multiple rejection rule. And then in this case, we call it the FBC procedure. And in this case, the number of false rejections is estimated by this. And we can also show that the procedure controls the FDR at level alpha. And in these two cases, again, we can define some E values in a similar fashion, and then we can show that if you apply the EVH procedures to these E values, at the end of the day, we will get the same set of rejections as the original FBH or FBC procedures. And indeed, we have a unified viewpoint. So indeed, most of the FDR controlling procedures will be equivalent to the EVH procedures. And we have the construction of the E values in this form. So the key is how you define the rejection rule and how you estimate the number of false rejections. But at the end of the day, we have a unified expression for the construction of the E values. All right, so why this is important and how can we use this insight? As I mentioned, E-value is a useful tool for combining results. And so here, let's consider a scenario where you have, let's say, 10 data sets. So for the first data set, it concerns about hypothesis 1 to hypothesis 10. For the second data set, it concerns about hypothesis 11 to 20, and so on and so forth. So you can think of this as the data sets from, let's say, 10 different labs, and each lab studies a particular subpopulation. And so you have different hypotheses, and then if a lab applied one of the multiple testing procedures, the lab can convert the results into a set of p-values based on the connection that I've just mentioned. And let's say if each lab apply a valid multiple testing procedure, then usually it means that for the corresponding p-values, we would have this inequality to ensure that the FDR is controlled for that particular data set. And then the question is, when we want to assemble these results together, we just have to, how can we assemble these results together? So basically, we just have to assemble the e-values and then apply the EBH procedure. And why do we want to do that? Well, here the reason is that we want to have a statistical conclusion that is valid for a wider range of populations. So for each lab, because the results is just for a subpopulation, right? So you can only claim the validity for that subpopulation. But if you assemble these data together, how can we claim that these things are valid for the whole population, for the bigger population? So basically what we did is we assemble those e-values and then we apply the EBH procedure. And because you have the procedure being valid for each subpopulation, when you assemble them together, the procedure is still valid, and the EBH procedure is going to control the overall FDR. And then another setup is that you have the same data set, and this data set, let's say, concerns about 100 hypotheses. You have let's say three different methods applied to this data set, then you would get three different sets of e-values. And so basically for the same hypothesis, you are going to get three e-values, right? Resulting from three different methods. And the question is, how can we combine the results from different methods? A simple way is just by taking an average of the three e-values concerning the same hypothesis. So here, if we have in general k methods, then you can take an average over the k e-values concerning the same hypothesis. And in this way, we can aggregate the results from k different methods. And if each method is valid, we can get these e-values over the ones that are under the norm. Summation will be less or equal to n. Then for this combined e-value, we still have this guarantee so that the EBH procedure can control the FDR. So in summary, so why do we want to combine the results? In the first scenario, we want to basically borrow information from different data sources so that you have a conclusion which is valid for a wider range of population. In the second scenario, we want to borrow strands from different methods so that you have a more robust and potentially more reliable results. And there's another scenario. In some cases, the method contains randomness, such as the knockout procedure. You have some kind of randomness in the procedure because of the design of the method. So by combining the results from multiple knockout procedures, you can reduce that randomness. So the results can be more stable. So let's think about a more concrete case. In the first scenario, so here, let's say you have two data sets. You have the data set concerning a male group and then a data set concerning a female group. So an analyst could analyze these two data sets separately and then can design a procedure which will control FDR for the male group and FDR for the female group. But then the question is that when we aggregate these results together, can we have a control over both the group one's FDR and the overall FDR? This is seemingly not a very difficult question, right? But it turns out that this problem has not been completely addressed in the literature. So here, on the one hand, we want to ensure that the FDR is controlled within each group because we want to achieve some kind of fairness. Let's say those hypotheses, they are related to certain high stake decisions like admission, hiring, right? So you want to ensure that for these two groups, the FDR could be controlled. And also you want to ensure that the overall FDR is controlled because you want to make sure that these decisions are valid for the whole population. And so you are not making too many false positives. So there are two naive procedures. The first one is that you can ignore the group structure and then just apply a multiple testing procedure to the whole data set. Then clearly you would not have guarantee for the group-wise FDR control. Another approach is that you can analyze these two data sets separately, but then you don't have the overall FDR control. So how can we achieve both? The idea here is not that complicated, simple. So what we did is we applied a multiple testing procedure separately to each data set, say the male group and female group. We got the results and then we convert the results into p-values. So now we have two sets of p-values. And then we assemble those e-values together. So now we have 100 e-values. And then we apply the EBH procedure. And we can show that the procedure is able to control both the group and overall FDR. And one of the innovation in our procedure is that we introduce some weights here, WI, to improve the power. So instead of using the naive weights, which is 1 in this case, we construct some weights. And the construction of these weights are actually very non-trivial. It depends on the argument we use. So to prove this result, we use the so-called leave one out argument. And by exploiting the proof, we figure out that there is a way to construct some weights so that we can still prove that the procedure controls the FDR. So this is one of the innovation in the methodology. So why do we use data-dependent weights? Here, I will give you a tall example for illustration. Let's say we have two groups. In group 1, there are 100 hypotheses. In group 2, there are 1,000 hypotheses. And then we apply the BC method, which identifies 20 significant features from each group. And if there are 20 significant features, that means when you convert them into e-values, there will be 20 non-zero e-values, and the remaining e-values are going to be 0. And by combining these e-values, by sorting them, we can then make a decision based on the EBH procedure. So at most, we can make 40 discoveries, at most. So in order to reject 40 features, we compare the 40th largest e-value with a data-dependent threshold. So in this case, the threshold only depends on the total number of hypotheses and also the FDR level, which is 5% here. So that threshold is 550. However, because for the non-zero e-values, we have 20 equal to 1,000, 20 equal to 100. So the 40th largest one is actually 100. So we are not able to make 40 rejections. And if we want to make 20 rejections, then we compare the 20th largest e-value with the corresponding threshold. In this case, the threshold is 1,100. But because the non-zero e-value, in this case, is equal to 1,000. Remember, we have 20 equal to 1,000 equal to 100. So the 20th largest one is 1,000. 1,000 is still below that threshold. So we are not able to make any rejections if we did not weigh these e-values. And so with weighting, essentially what we did is we increase those smaller e-values and decrease those larger e-values. And at the end, after weighting, those e-values, they will be the same. And when you compare the 40th largest e-value with the threshold, it turns out that it's bigger than that threshold. And in this whole example, we are able to reject all of them. So that's the rationale behind the weighting. But it's not guaranteed that in every for every data set, we can always achieve this improvement. But at least in some of the simulation runs, we saw this. And eventually, it will lead to some power improvement compared to the naive weighting. And so here are some simulation results. here we compare our approach with two other naive approaches, as I mentioned. The first one is that we just ignore the group structure and apply the BC procedure to the whole data set. And clearly, by ignoring the group structure, we are not able to control the group-wise FDR. And this is the same because for the second group, the FDR is bigger than the 5% level. And the second approach is that we apply the FDR method to each group separately. And you can see that in this case, the overall FDR is not controlled, it's about the 5% level. And by using our approach, we can control both the overall and the group-wise FDR. And the power in this case is reasonable. So that's the first application. And let's get into the second one. So this is related to how we can combine the results from different methods. So let's say we have two multiple testing procedures, procedure A and procedure B. So they're applied to the same data set. For procedure A, we apply it to the data set with some level, say alpha A, and then we can get a set of E values. For procedure B, we can apply it to the same data set with the level, say alpha B, and then you can get a set of E values. And to combine the results from these two different procedures, basically what you have to do is to take an average. And here we do a more delicate combination. We use a weighted average. And again, those weights will be complicated based on the leave one out argument. And then the idea is that we just run the EH procedure on these E values in order to combine the results from procedure A and B. So one example is that you have choose procedure A to the BH procedure and then procedure B to the BC procedure. And then you can choose the weights in this way. Again, the design is very non-trivial. It's based on the proof. So you have to carefully design this weight such that the proof can go through. And with this design, we are able to show that the EVH procedure controls the FDR. So why do we want to do that? As I mentioned, we want to achieve some kind of robustness. And the reason is that for the BH and BC, usually none of them dominate the others. There are scenarios where the BH procedure performs better. There are also scenarios where BC procedure performs better. Although in most cases, I think the BH procedure indeed performs better. So in this simulation, we consider a scenario where the BH procedure outperforms the BC procedure. So if you look at the power, you can see that the red curve is above the curve associated with BC procedure. So it's better. And here we compare BH, BC with a naive approach where we just take a usual average, so the weights are 0.5. And then the one with data-driven weights, which is the one we propose. And then we have a fast implementation of our method. So in terms of power, you can see that our approach achieved the power almost identical to the BH procedure and is much better than the BC procedure in the simulation example. And all the procedures are able to control the FDR at the desired 5% level. And here is another application simulation example. So in this case, the BC procedure is better. It's more powerful than the BH procedure. And with our method, we achieve a power which is in between the BH and BC. It is, of course, in this case, much better than BH in terms of power. And again, our procedure is able to control the FDR. So you may wonder, maybe you can do this. So you try both procedures and see which one give you more rejections, and then you publish the results. But that is not valid. So this is sort of like treating. And indeed, if you do that, you will see that the FDR is not going to control. So if you always choose the one with more discoveries, it's like a data manipulation, and at the end, the FDR is not controlled. So you cannot do that. And of course, I believe that there are other applications that you can do. For example, if your procedure has a tuning parameter and you don't know how to choose the tuning parameter, then one way to do it is by aggregating the results. So you can choose a set of tuning parameters. For each tuning parameter, you got the results, and then you combine the results through e-values. So in this way, you can reduce the impact of the tuning parameter result. And one final application, I'm going to talk about covariate adaptive multiple testing. So this is particularly motivated by applications from genomics in GWAS, microbiome-wide association studies, EWAS. We often have some external information. So for each gene, we not only have a p-value, but often we have some external information which can be summarized in terms of a covariate for each hypothesis. So in this setting, besides the p-value, pi, we also have xi covariate for each hypothesis. And then the question is, how can we utilize those covariate in order to develop a procedure that is more powerful than the one without using covariate? So in microbiome association studies, we often have the so-called group structure or the more delicate phylogenetic information, which summarize the relationship between different OTUs, how they are related evolutionary. And in spatial applications, the hypothesis could be associated with different spatial locations. And a natural assumption is that when those hypotheses they are close in terms of spatial locations, then they are more likely to be all significant or all insignificant. So we have the spatial information. And then in some other applications, we may have the so-called ordering information. We can order the hypothesis from the less promising one to the most promising one. So the external information in general can affect the chance that the hypothesis is being true. So just think about the scenario where you have two groups, and in one group you have a lot of signals, in the other group you have a very small number of signals. Then this group information is certainly useful for determining the chance that the particular hypothesis is being significant or not, right? And then in some applications, the external information may be related to the signal strength. For example, you can use the sample size sometimes as the external information. So here the sample size is related to so-called sequencing depths in genomic applications. And if the sequencing depth is large, usually it means that if the hypothesis is under the alternative, the signal could be stronger. And so the goal here is we want to incorporate the external structure information to improve the statistical power. But then on the other hand, we of course also want to ensure that the FDR is controlled. So the approach we consider here based on the idea of cross-fitting. And again, it's related to the e-value idea. So let's say we have a big data set concerning, let's say, a large number of hypotheses. So what we did here is we divide the data set into some subsets. So you can divide it into, let's say, 10 subsets. So this is sort of like tenfold cross-validation. So what we did is if you want to perform hypothesis testing for a subset, then we use the remaining data set as the data estimate Fi. So remember here, Fi is the function that determines the threshold for each hypothesis. So remember when I talk about the FBH and FBC procedure, there is an Fi there which determines the threshold. So the threshold is FIT. And so there I didn't mention how you can actually estimate that Fi. And here is the setup where we can actually estimate Fi from the data. So if you have an hypothesis I in, let's say, this group, then we are going to use the renaming groups to estimate that Fi. And usually you have to assume that this Fi has some structure. Otherwise, it's too liberal. So for example, you can assume that Fi is actually a function of your external information xi. So then that's why we have an index I here. And also is parameterized by beta, which is the parameter we want to estimate. And so without using the data in that particular yellow group, we can estimate beta by, for example, minimizing some kind of loss function, which could be the negative log likelihood. You have some kind of pseudo likelihood. You estimate that beta, and then you plug in beta, you can get your Fi hat. And then with this Fi hat, you can have a data-driven threshold for I's hypothesis in that yellow group. And you can perform multiple testing using some multiple testing procedures. So again, here I'm going to use the BC procedure as an example, but you can also use FBH. So in this case, once you get Fi hat, you can perform multiple testing on that particular group, and you can convert the results into some p-values. And again, we can allow some kind of weighting here. And so you have the testing results for each group, right? So you can loop this procedure. So you can perform testing on the first group using the other groups to estimate Fi, and then you can do the same thing to perform multiple testing for this group using the other group to estimate Fi. Right? So that's why it's called cross-fitting. And then at the end of the day, you are going to have multiple testing results for each of these yellow groups. You have looked over all the data set, and then you have the testing results for individual groups. And then the question is, we want to assemble things together, right? And because we have p-values, so it's easy. We can just assemble the results, and we can apply the EBH procedure to the set of p-values. And we did some simulation, and what we found is that the FDR really is where control for this procedure. Indeed, in theory, we prove that it can control the FDR. So this is consistent with the theory. And in terms of power, there are already some competing approaches in the literature, but we found that our approach indeed performs quite competitively with those existing approaches. So you can see that in this simulation example, it's actually more powerful than the other methods in most of the cases. So in general, we see that it's one of the most powerful approaches comparing to the other approaches. Okay, so finally to conclude, I want to mention that this idea is a high-level idea. It's useful for aggregating results, assembling results, and I believe that it could be also applied to other settings. So right now, we're exploring the use of this in the so-called replicability analysis, and I believe there might be some other settings you can consider. One issue with the current implementation is that we use the so-called data-dependent weights, and those weights, they are constructed based on the lib1 argument. So in order to implement that, we actually have to repeatedly apply the procedure many times, so it can be computationally inefficient. And an important question is, how can we design a more efficient method to implement the procedure? And another question is, for now, all the theory we developed is under the independence across the p-value sequence. But we know that for the EBH procedure, by design, it's robust to arbitrary dependence. And the question is whether we can prove that the procedure can actually control the FDR under some kind of dependence. Okay, so the talk is based on these two papers. I think you can find them. You can find them online. And thank you for your attention.
Any questions?
Yeah, thanks for the nice talk. This might be a very naive question, but since I'm new to those kind of e-value concepts, basically, as far as I understand, I think e-value is constructed based on the Markov inequality, but usually it's known that like Markov inequalities are very loose inequalities. So like if we have more assumption on distribution, for example, if we know they follow sub-Gaussian, can we construct e-value that's kind of more tight
Yeah, that's a very good question.
And is that helpful if we construct a tighter e-value?
Yeah, I think definitely that's something very interesting. So, for those who have taken the course, you actually done some simulation to show that if we use the e-values, the power is lower than using likelihood ratio tests. And I think exploring the tail behavior, I think that's interesting. You can possibly construct some e-values by exploiting the lighter tail. Maybe you can get better results.
Any more question? Then let's think.